All right, we're back, and we're just about to nail this Bayesian Naive Bayes classifier. And so last time I made a little flub here. I kept the k, but I dropped the product over k's, and I should have made this a y because we only kept the ones where k equaled y. So then down here, this should be, let's see, this should be a y, and this should be a y. Y, and that's y. And let me just verify here that I sort of claimed, or I gave a little justification for why the sum of these was equal to cy. But let me give you a little bit more formal argument here. This is the sum of indicators. Well, let me put it up here so I have room. This is the sum of indicator functions from as I goes from 1 to n, that's all our data points. The indicator that xij equals L times the indicator that yi equals k. And so let's take that, and we'll remember that and write it down here. We'll do this sum. So this is a little aside. The sum over L djk of L is the sum over L of the sum over I from 1 to n, indicator xij equals L times the indicator that yi equals k. I think that was what it was, isn't it? yi equals k, xi, right. And here the sum over the L's is, let's see, what is L is all the possible values that x might take, right? So that's L from 1 to, I think we said capital N. Okay, and now if we switch these sums, we can always do that because these are just finite sums here. So if we switch the sums, then inside, well, what depends on L? Only this one. So we get a sum over I from 1 to n. We can pull out the indicator for yi equals k, and the sum for sum for L moves in, and that's this indicator, sum over L of the indicator that xij equals L. But this is just, and every feature xij equals L for some L. So this and it equals some L for some L and exactly 1, right? It just takes only one of those values, so this is just 1. And so this whole thing is just the indicator over i's of, or the sum over i's of indicator that yi equals k, and that's just the number of i's such that yi equals k. And so this was cy. That's what we defined to be cy. Number of i's such that y equals k. Okay, so that was just a little side note, just to verify that that little argument. All right, I think we've got it now. So we had, this was our predictive distribution. That was the thing that we needed to get our hands on to do our classification, and we got this, well, at least proportional to this nice little expression. And let's write it all out. Let's write out what we got here, just to make it all satisfying result. So the predictive distribution, posterior predictive distribution, is proportional to alpha y plus cy divided by alpha 0 plus n times the product over j from 1 to d, the betas, beta xj plus djy of xj divided by beta 0 plus cy. That is our result. And this is a beautiful thing because, well, let me say first why this proportional to is satisfactory because remember that in order to do classification, we want to predict a y hat that maximizes this probability. So over all y's, we want to choose the y that maximizes this predicted distribution. That's our optimal choice of y to minimize our misclassification rate. And since this is proportional with respect to y, then maximizing something which is proportional is the same as, as long as it's positive proportionality, in this case it is, maximizing that is the same as maximizing this thing. And so we can just take the maximum over this expression, the y which maximizes this expression, and that gives us the same value, y hat. So this is it. This is our beautiful Bayesian, fully Bayesian classifier for naive Bayes. So let's go back through real quickly and remind you what made this a Bayesian approach and what were the key steps, so we can sort of understand what's going on here. So the naive Bayes part was just this original setup here, where we had the features were conditionally independent given the class and given theta. And then we put some priors down. We put some priors down on our parameters. That was this part here. These were our priors. And then, so that was the first step to being Bayesian, was we put some priors. And then we wanted to compute this posterior predictive distribution. So the next thing was we integrated out our parameters. And in a fully Bayesian approach, you actually do the integral, or that's the ideal thing, rather than just approximating it by a point estimate like in MLE or MAP. To be fully Bayesian, you integrate out your parameters, and we're doing that here. So we were integrating these out, and we wrote down these expressions for the different parts of the integral. And then we got down to this. So this step, this was the key. This was really the key, one of the key things that made the computation work. We used the fact that the Dirichlet is a conjugate prior for the categorical. And so we could express these as, oh wait, that shouldn't be equal. That's an error. That should be proportional to. This is proportional to as a function of pi. And so the reason why that's sufficient. So this is the Dirichlet categorical conjugacy, and that was a necessary step. And this is proportional to this with respect to pi, and it's also proportional with respect to y. Y doesn't show up in here at all, right? These are all just the y. Oh yeah, y does. Yeah, right. It's proportional with respect to y also, because these yi's were our data points, and this is the y that we're going to choose to classify. So that this y doesn't even show up in this expression, so it's obviously proportional with respect to that. And the reason why this is okay is that, back up here, as long as, so that was our A here, and as long as this is proportional with respect to y and theta, it also needs to be proportional with respect to theta, because we're integrating over theta. So it's okay, even though this is inside the integral, it's okay that this is just proportional, because the constant of proportionality, since it doesn't depend on theta, it comes out of the integral. So if right, that's the reason why. Okay, so sorry about that little misstep there. So this was a really a key fact in this derivation, was that the Dirichlet is conjugate prior, and that allowed us to express the factors in this integral in closed form in terms of these Dirichlet distributions, these densities. And then the other key step was not only that we could get that posterior distribution on the parameters, that was what we did here in this A. Basically this was getting the posterior distribution on the parameters. That was basically what we were doing. And then down here, the other key thing which made this work was that we were able to analytically compute this integral. And the reason why we were able to do that was just because the values that we were integrating over were just values of these categorical distributions, and so these just turned into nice little expected values that we could factor this whole thing. There was no dependencies between them. Everything factored beautifully, and we could just write down some nice and easy expressions for these means of these Dirichlets. And that was what made it all work. Those were sort of the key steps that made this whole Bayesian naive Bayes approach work. So this is in some sense the ideal situation for this is an ideal case for a Bayesian type of approach, because it's most of the time, or a lot of the time, we won't be able to get an exact expression for something which is proportional to what we're looking for, like the posterior predictive. We'll only have to settle for some approximation. But this is a great example, this Bayesian naive Bayes, to illustrate the main ideas of Bayesian inference in a real situation. I mean, this is a classifier that it does something real. This is a real example. This is Bayesian inference. All right. So we'll stop there, and we'll leave it at that for our Bayesian naive Bayes.